If you watched my previous video, we did the percent composition of sugar in bubblegum as kind of an application before we dive into the chemistry of what percent composition is in terms of chemistry. By the end of this video, you should be able to solve percent compositions within the context of chemistry, that is. So let's first define percent composition. Percent composition is the relative amounts of elements within a compound. So we're looking at the specific amount of one type of atom in a compound versus the entire compound, including that atom. As a reminder, a compound is composed of two or more different elements, and so we can pick apart which atom we want to figure out what percentage of that compound is that atom. Therefore, then, we can figure out how much of each element present can be measured as a percent within that compound. So for example, from the sugar in the bubblegum lab that we did before this video, we saw, okay, for example, if the piece of gum itself weighed 6.1 grams, and then the sugar, after you chewed the gum and sucked out basically all of the sugar, and were left with the nasty double bubble rubber at the end, basically, then we figured out, okay, then that mass difference was 3 grams for sugar, supposedly. So that would be the part per the whole in order to determine our percent composition of sugar. Now, if we're going to think about this in terms of chemistry, however, we're going to look at this in terms of HCl, hydrochloric acid. HCl has one H that has a mass of 1 from our periodic table, and 1 chlorine, which has a mass of 35, that's rounded, from our periodic table. And if we wanted to know what the percent composition of chlorine was in hydrochloric acid, in HCl, we would take the part, the chlorine, at 35 grams per mole, divided by the hydrochloric acid altogether, which would be 36 grams per mole. When we do that and then multiply by 100 to get that decimal into a percent form, we would end up with 97.2% of HCl is chlorine. So we can do this for any compound in chemistry. Before we begin through the steps of how to do percent composition, always assume the total is 100%. You don't want to go under that, you don't want to go over that. Assume the total is 100. Step 1 is to look at your periodic table to find the molar mass of each atom present. So for each element type, each atom type present, you want to know what its individual mass is. And at this point, it's a really good habit as your first step to just list out all of the atom types present, like HCl, and then write their mass next to it as you go. So you don't have to keep going back to the periodic table if you don't want to. Step 2 would be to find the molar mass for the entire compound. If you don't know how to find molar mass, please check out my previous video on molar mass, linked in the description below. And that number will be your denominator. So after you add up all the pieces in the whole compound from your periodic table values, that's going to be your denominator. Step 3 is then to divide the individual element's mass, so the specific atom you're looking at, by the total mass of the compound. So any individual element mass or atom mass that you're interested in is going to be in the numerator of your division setup. So as you can see here, the mass of an element in 1 mole of a compound, because we're talking about grams per mole, again, that's the value from the periodic table, our AMU, atomic mass unit, divided by the mass of 1 mole of the total compound. That's our molar mass of the compound, times 100 equals percent comp. So let's walk through this example first before we jump into doing some calculations of our own. We're going to find the percent composition of calcium carbonate. That's the same stuff that's in Tums that helps your tummy, your stomach acid, when you're feeling a little heartburn coming on or anything like that. It's also the thing that makes up a lot of oyster shells and like seashells and stuff like that in the ocean, calcium carbonate. So if we wanted to find the percent composition of each of the atom types present, so the Ca, the C, and the O, we would just look on our periodic table and find that calcium's mass is 40.08 grams for just the calcium atom, and the entire molecule of calcium carbonate is 40.08 plus 12.01, that's the carbon, plus 3 of the oxygen, so 3 times 16 times 100. So that would give us 40.04% by mass for just the calcium. For carbon, the carbon atom weighs 12.01 grams per mole. and the entire molecule is the same denominator as the calcium problem set up before. Times 100 gives us 12% by mass. And lastly, we have oxygen. There's 3 of them, so our numerator is going to reflect that in 3 times 16 oxygen atoms, divided by the same denominator as was in the first 2, because it's still the same compound, times 100, and that gives us 47.96% composition of oxygen by mass. This beautiful little molecule over here is called sucrose, and I want to know what the percent composition of each atom type present is in 1 molecule of sucrose. So our molecule formula is up here, C12H22O11. We're going to have a carbon, we're going to have hydrogen, and we're going to have oxygen from the periodic table. So our first step is looking at that periodic table as we just did, finding all of the element atom types present within our molecule, and now we're going to list them out. We're going to say, okay, hydrogen, carbon, oxygen. Hydrogen's mass is 1.008, carbon's mass is 12.011, and oxygen's mass is 16. I'm just going to round up the 15.99. The second step is to figure out what the entire molecule's molar mass is. We need to know the whole before we go back to the parts. So in the whole molecule, we have 22 hydrogen atoms, we have 12 carbon atoms, and we have 11 oxygen atoms. When we multiply those all out, we get the following answers: 22.176, 144.132, and 176. Now, as we learned in our previous video about how to find molar mass of a compound, we need to add up all of these together. So our final answer after adding these all together is 342.308 grams per mole as our molar mass for the whole compound of sucrose. Step 3 is to now take all of our individual parts and divide it by the whole. What's really convenient about how we've set this up is that we already have the parts done. So as long as you wrote them out beforehand and had good bookkeeping skills, it should be really easy now to just go back and divide each one of these values by 342.308. All right, now that I've set those all up for you, all I did was take the part for each one and divide it by the whole. Notice that for each one, I didn't just keep 1 oxygen, so I didn't just say 16 for the mass of 1 oxygen divided by 342. That's not what we have to do. We still have to account for the fact that there's 11 oxygens. That's why we keep that 176 there. So now if I go through and divide these, I get very small decimal values. I can't just leave it as a decimal value. We're trying to find percent, remember? So I have to multiply these all by 100 in order to get it out of the decimal format and into a percent format. So if I multiply by 100, essentially I'm just moving the decimal over 2 spaces, and that would give me 6.5% roughly. 1, 2 would give me 42%, and 1, 2 would give me roughly 51.4%. Now, if you were to add all 3 of those percentages together, they should be very close to 100%, if not exactly 100%. I just add them all together for you, and it's 99.9%. That's close enough. We know that we did it right. This is a good way to check your work and make sure that you did get the answer correct if it's close to 100%. Go ahead and pause the video here and try and solve the percent composition for each atom type in morphine. That's a painkiller like ibuprofen. And my personal favorite when I was in the hospital was shigellosis at one point. Oh, you don't know what shigellosis is? Neither did I. I had food poisoning from Mexico when I went there on spring break and ended up in the hospital for like 3 or 4 days, something like that. I went to urgent care and the lady there was like, "Oh, you're fine. You're fine. You're not dehydrated." And then by the time I made it to the emergency room, they had to pump in like 4 bags of IV into me just to stabilize me. But I wasn't dehydrated or anything. With shigellosis. Seriously, it's a thing. Look it up. And morphine's pretty much the only thing that helped me kill all the pain while I was there. Now that I have thoroughly bored you with that side note, go ahead and really pause the video now and give this one a try. All right, let's check your answer. Make sure you got it right. Our morphine molecular formula is right here. So we know right away we've got carbon atoms present. we've got nitrogen atoms present, we've got oxygen atoms present, and we have hydrogen atoms present. Let's list them all out. Carbon brings to the table a mass of 12.011. Hydrogen has 1.008. Nitrogen's mass is 14.007. And oxygen, as always, is 16. You can keep it as 15.999 if you like to torture yourself. Otherwise, just round it up to 16. We see from above that we have 17 carbon atoms. We have 19 hydrogen atoms. We have 1 nitrogen atom. And we have 3 oxygen atoms. Go ahead and do all those multiplications in your calculator. For carbon, we end up with a 204.187. For hydrogen, we end up with a whopping 19.152. Of course, anything times 1 is just going to be itself. For nitrogen, we just have 14.007. And finally, for oxygen, we have 48. Now we need to figure out what the whole is. We have all the parts, what's the whole? In other words, we're solving for our denominator. We're going to add up these 4 values together. After adding up those 4 values, we end up with 285.346 grams per mole for the entire compound of morphine. Now, conveniently, since we've set up everything nice and orderly, and we have good bookkeeping skills for chemistry, we can just take all of our parts and divide it by the whole that we've already calculated. So we're just going to take our 204.187, divide it by 285.346, and divide all of them by the same value, 285.346. Let's go ahead and divide this in our calculator. For carbon, we end up with 0.715. For hydrogen, we end up with 0.0671. And notice how I don't just say 0.0671 or 0.715. I always include that 0 in the front. Why? Why do I do that? It's a good habit, a good bookkeeping skill for numerical values, because then you know that there's a decimal in between the zeros, and you'll never lose a decimal on accident. For nitrogen, I end up with 0.0491, and for oxygen, I have 0.168. Now, just like before, I could take these numbers and literally multiply them by 100 in my calculator. That is an equally valid way to solve this problem. Or I can just move my decimal over to the right 2 spaces, for 100 having 2 zeros. So 1, 2 would give me 71.5%, and 1, 2, 6.71% for hydrogen, 1, 2, 4.91% for nitrogen, 1, 2, 16.8% for oxygen. Now I've got all my percent compositions for each atom type present within 1 molecule of morphine. By the way, my husband still teases me about that instance in the hospital because he said that I was so doped up on that morphine, I was just like a complete train wreck and acting super goofy. But I guess that's what the poppy flower can do for you. Again, as a final check, I would always take these numbers, add them up, and make sure that you get somewhere close to 100 to make sure that you did the question correctly. Now's the time to check yourself before you wreck yourself. Go ahead and pause the video here and see if you can answer the following 4 questions on percent composition and all the atom types present within those molecules. There's an added challenge here in that you have to take the words of chemicals and turn them into their ionics formula first before you can solve for the percent composition. If you're not sure how to do that, be sure to check out my previous videos on naming ionic compounds linked in the description below. That's all for today, ducklings. Please give me a quacks up and make sure you subscribe to my channel if you haven't already to help others like you find my content if it happens to be helpful for you. So long, have a ducky day.
No ducks, no glory.